Hello everybody, Mr. Brown here, and in this presentation we're going to talk about section 1.4 from your textbook, where we begin to cover measurements in chemistry. At the end of this presentation you should be able to explain the magnitude and unit parts of a measurement, use scientific notation to simplify very large and very small numbers, convert measurements between units using the SI system of measurement, explain density and how it is measured, and use the density equals mass divided by volume formula to determine the mass, volume, or density of a sample given the other two variables. Okay, to start with, we're just going to take a few minutes to talk about what makes a measurement, what differentiates a measurement from just any everyday number. And that differentiation comes in what we call a unit. A unit is usually a letter following the measurement that you see or take in an observation or a data point or something. And that unit tells you what is being measured and gives you information about how much of that measurement, what the unit does as a standard to compare that measurement to. And so we have some examples here on the slide. We have the first one is one looks like one that you will probably see quite a few times during your course in the lab portion of this class. Something that looks like 47.34 G, looks like a measurement that you would take off one of the electronic balances, and of course G here stands for grams, which is our standard unit of mass. I have another example there with the 119.32 km, and that measurement is a measurement of distance. It is a measurement of 119.32 kilometers or kilometers, and if you don't know, that's how most of the rest of the world would measure something like we measure in miles. So we're talking about almost comparable distances between kilometers and miles. And so you would see that on a road sign somewhere other than the United States, other than the picture I have there. That is actually a picture of a highway in Arizona that they have some kilometer road signs for distance on them. And then down there at the bottom I have an example of just a number, 43.90238. It's not a measurement. We don't really get a lot of information from whatever that number is telling us because there is no unit. So all of this is just to say units are one of the most important parts of the measurements that we take in science, and don't forget to include the units when you're writing your numbers down. You'll be reminded of that a lot in this class. Something else that you will run across that you may or may not be familiar with will be some scientific notation. Scientific notation is a way that scientists have come up with to more cleanly write very large or very small numbers. When you have some data points have many decimal places or are rather large, so we like to find ways to contract those numbers and, quite frankly, just make them less to write. So I have some examples of how scientific notation works on this slide. You can see if we had a large number like 136 million, we could also express that instead as 1.36 times 10 to the 8th. Or alternatively, you may see it written sometimes as 1.36 E8. And the E is just a shorter abbreviation for times 10 to whatever number you see there. Alternatively, we can also use scientific notation to make very small numbers a little bit easier to write as well. For instance, we have the number 0.000000000567 down here. And so in the interest of shortening that number up, if I have to write it a bunch of times, we've converted it into scientific notation. That number would be 5.67 times 10 to the negative 10, or 5.67 E negative 10. And so we can see some rules for using scientific notation down here at the bottom of the slide. To convert numbers to scientific notation, you take the decimal and move it right or left until you have a single digit number. To that single digit number, you add 10 times 10 to the n, with n being the number of decimal places you moved. If you move the decimal left because you were converting a large number, then your n should be a positive number. If you move the decimal right because the number you were trying to convert was a very, very small number, then n should be negative. Here on this slide, we have instructions for converting numbers already in scientific notation to a more normal looking format. To do so, you're going to simply move the decimal places the number of spaces indicated by the n. You're going to move the decimal to the left if n is negative, and you're going to move the decimal to the right if n is positive. And then you will use zeros to fill in any of the empty spaces left over. We have two examples here on the bottom. 2.34 times 10 to the 5th could be written out also as 234,000. 8.4 times 10 to the negative 7th would become 0.00000084. On the next slide, I'll work out some examples of these if you would like to follow along. On this slide, I'm going to work some examples of converting numbers in scientific notation into standard format. And so we'll start with the first example there. We have 1.8827 times 10 to the third. So the positive number in the exponent place will tell us to move our decimal place right. And we're going to move it a total of 3 spaces. So we'll pick up our decimal and move it 1, 2, 3 spaces to the right. That number now becomes 1882.7 or 1882.7. The next number, 5.3483 times 10 to the 10th. So again, the positive number is going to tell us to move our decimal place right, and we're going to move it a total of 10 times in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Replace it. We'll fill in any empty spaces with zeros. And so 5.3483 times 10 to the 10th becomes this big number, 53483 followed by 246 zeros. Our next example is 4.3 times 10 to the negative 4. So this time the negative number is telling us to move our decimal to the left. We'll move it 1, 2, 3, 4 spaces as indicated by the 4. Fill in zeros in empty spaces. And I personally like a 0 in front of the decimal as a placeholder. So 4.3 times 10 to the negative 4 becomes 0.00043. The next one asks us to convert 9.31 times 10 to the 5th. So we will put our 9.31. This time our exponent is positive, so we will move our decimal place to the right 1, 2, 3, 4, 5 times. And replace our decimal, filling in the empty spots with zeros. That number becomes 931,000. The next one asks us to convert 1.29 times 10 to the 7th to standard format. So we'll write our 1.29. Again, this is a positive exponent, so we're moving our decimal to the right 7 times. 1, 2, 3, 4, 5, 6, 7. Replacing the decimal and filling in the empty spaces with zeros. So 1.29 times 10 to the 7th becomes
12,900,000 it looks like. The next, 9.38372 times 10 to the negative 2. We'll write our number. We'll note that this is a negative exponent, meaning we want to move our decimal to the left. 2 spaces goes 1, 2. Place a 0 in the empty spot. So that number becomes, and again, I like a 0 in front of the decimal as well, 0.0938372. The next one is 8.4 times 10 to the negative 12. So I'm going to give myself a little bit of room over here. 8.4. This is a negative exponent, so we're moving our decimal left. We got to move it 12 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That got tight. We'll put a 0 in front, and zeros all the way down. Looks like there will be 11 of them. And so our 8.4 times 10 to the negative 12 becomes 0.2468 10, 11 zeros, followed by the 8, 4. Similarly, 7 times 10 to the 16th here, we'll write a 7 here. Our decimal is here, even though it's not represented. And we're moving in a positive direction to the right in this example, but we got to move for a total of 16. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, I believe. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 zeros will follow our 7, making our whole answer that big number 7 followed by 16 zeros. The next example, 3.22 times 10 squared. We'll move our decimal place right in the positive direction, 2 spaces, giving us 322. And for the final example, we have 2.4 times 10 to the negative 5. We have to give ourselves some space. So if we take that decimal and move them in the negative direction to the left, 1, 2, 3, 4, 5 spaces. Fill in the empty spaces with zeros. That answer becomes 0.0002024.
And I'm not, hold on. For our first example, we will convert 3,000 grams to how many kilograms? We write our base number down, 3,000. We put our decimal here. And then we move our decimal the number of places that it takes to get from grams to kilograms and in the same direction. That would be 3 spaces. 1, 2, 3. That means 3,000 grams is equal to 3.0 kilograms. You could also do the same conversion by showing that 3,000 grams divided by, there are 1,000 grams in a kilogram equals 3 kilograms. On this slide, we see her converting 3.5 kilometers to meters. So we write down our 3.5 km. We're trying to convert that into meters. We know that there are 1,000 meters in a kilometer, and we can see that there are 1, 2, 3 jumps between kilometers and meters.
So we can write 3.5 out, put 1, 2, 3 jumps of our decimal place to the right, fill in the empty spaces with zeros, and then we come to the understanding that 3.5 kilometers is equal to 3,500 meters. This problem asks us to convert 45 milliliters to liters. We will write our 45 down, put our decimal even though it's not shown. We count and see that to go from milli to the base unit liters, we have to make 1, 2, 3 jumps to the left. So we will take our decimal and move it 1, 2, 3 spaces to the left and replace it. Fill in empty spaces with a 0, and I personally like to put a 0 in front of the decimal just for posterity. So that leads us to see that 45 milliliters is equal to 0.045 liters. This problem asks us to convert 138 liters to deciliters, so we will write down our 138, put our decimal, and see that to go from the base unit liters to deciliters, we need to make 1 jump to the right. We will move our decimal 1 jump to the right, fill in the empty space with a 0, and that leads us to see that 138 liters is equal to 1,380 deciliters. Here we are asked to convert 18.3 meters to kilometers, so we will write 18.3 down. We see that to go from the base unit meters to kilo, we need to move 1, 2, 3 jumps to the left. So we take our decimal and move them 1, 2, 3 jumps to the left. We replace him and we add in zeros. I like to put a 0 in front of the decimal as well. We see that 18.3 meters is equal to 0.0183 kilometers. Here we are asked to convert 634.87 grams to hectograms, so we will write 634.87 down. We see that to go from the base unit grams to the hectogram, we need to move 1, 2 jumps to the left. So we will take our decimal and move it 1, 2 jumps to the left. It turns out that 634.87 grams is equal to 6.3487 hectograms. Here on this slide, we are asked to convert 6.38 times 10 to the 6 meters to kilometers. This is a little bit different than the other ones we've been asked because we're given a number in scientific notation and asked to convert in between units. And so there's two ways we could approach this. We could write down our 6.38 times 10 to the 6th, and we could remember that in scientific notation that moves of our decimal will actually change this number right here. And if we move our decimal to the left to go from millimeters to kilometers, then that would be 3 jumps to the left, which would reduce that number by 3. And therefore 6.38 times 10 to the 6 would become 6.38 times 10 to the 3rd kilometers. Of course, we can do it sort of the old-fashioned way where we just expand the number to normal notation and then do our conversion, which is what I'll show you here. So if we have 6.38 times 10 to the 6th, we expand that out to a normal number by writing our 6.38 and moving our decimal places 6 places to the right, since that is positive. 1, 2, 3, 4, 5, 6. And placing our decimal, we'll fill in those empty spaces with zeros. So 6.38 times 10 to the 6 becomes 6,380,000. and that is in meters. So we'll rewrite that, 6,380,000 meters. And if we want to go from meters to kilometers, we see our base unit is here, and we're going to move that decimal 1, 2, 3 jumps to the left. So we'll take our decimal here and move it 1, 2, 3 jumps to the left and replace it. So 6,380,000 meters becomes 6,380 kilometers, which is the same thing that we showed above, 6.38 times 10 to the third kilometers. On this slide, we're asked to convert 8.43 times 10 to the negative 5 grams to milligrams. Once again, we could write down our scientifically notated number, 8.43 times 10 to the negative 5. And if we went from grams to milligrams, that is 3 decimal places to the right, which will actually increase this number here by 3, and that would become 8.43 times 10 to the negative 2 milligrams. Of course, we can expand that out and show that to be the case. We can write our 8.43 down. And to expand it out, the negative 5 tells us to move our decimal place to the left by 5 positions. Replace our decimal, write 1 in front, and then fill in the empty spaces with zeros. So 8.43 times 10 to the negative 5th grams becomes 0.0000843 grams. And we're going to take that number and then convert it into milligrams. So I'll rewrite it down here, 0.0000843 grams. And again, we've noted that to move from the base unit grams to the milligram, we need to make 1, 2, 3 decimal jumps to the right. 1, 2, 3 decimal jumps to the right. So 0.0000843 grams is the same as 0.0843 milligrams, which, as we showed above, is the same as 8.43 times 10 to the negative 2 milligrams. This question asks us to convert 650 nanometers to meters. This is a little bit tricky, I guess, because nanometers is a very small prefix. You may notice it's not listed on our handy jump chart down here at the bottom. In fact, nano lies 6 times below, or 6 orders of magnitude below the milli prefix. So 6 more spaces down this way. And we're asked to go from 650 nanometers to meters. And so if we wrote our 650 down, and actually we may need more room than if we wrote our 650 here, we put our decimal here, and we considered that we'd have to take 6 jumps to the left to get to the milli spot, and then from the milli spot we would need to still go 7, 8, 9 jumps to get to the base spot from to the meter. So we would move our decimal place that 9 spots to the left. We would take it and go 1, 2, 3, 4, 5, 6, 7, 8, 9. I like a 0 in front, and fill in our empty spaces with zeros, making our 650 meters, or sorry, nanometers, equal to 0.000000065 .50 meters. So a very, very, very small portion of a meter. This slide asks us a little more straightforward question. We're going to convert 897 milliseconds to seconds, although we might not be so familiar with conversion in time. Just like always, we're going to write down our 897, determine how many decimal jumps we're going to make to go from milli to seconds. Seconds would be a base unit. We're going to make 1, 2, 3 jumps to the left. So we'll take our decimal here. 1, 2, 3 jumps to the left. And 897 milliseconds becomes 0.897 seconds.
Now that we've had a little bit of a review or perhaps a fresh look at the way that measurement are handled and taken in chemistry, particularly how units work and the units that we work with in the scientific world, we're going to start to explore how we mix some of those units to evaluate different properties of matter. The first one that we always start with here is density. Remember, density is an intensive property of matter that describes the ratio of an object's material's mass to its volume. And so basically what that's saying is density describes how much different materials pack into their given spaces. And remember that intensive means that it will not change with the difference in size and samples of this substance. For instance, the density of water in a cup of water sitting on your table is the same density as all of the water in all of Earth's oceans. That being an obvious size disparity in the samples, they still have the same density, whereas the mass of the water in the oceans is much, much, much more massive than the mass of the water in the cup, for instance. Having a high density means that more matter is packed into a smaller space, and vice versa. Having a low density means that a large space is occupied by relatively small amounts of matter. When I usually teach density, and you'll probably hear me say this again in lab, I always ask my students to do just a quick thought experiment. Imagine you had two baseball-sized balls, one in each hand, and one was made of lead and the other was made of styrofoam. It's easy to imagine the lead ball being much, much heavier than the styrofoam ball, and that's because lead is a much more dense material than styrofoam. Density can also give you an idea about whether or not a material will float in another substance, particularly water. Water has a density of 1 gram per milliliter that we'll explore a little bit further on the next slide. But anything that has a lower density than that will float in water, and anything that has a higher density than that will sink in water. You can see the density formula on this slide. It's given to you as density equals m over v, density being represented by this weird symbol. That's a Greek letter rho. On most of my stuff, I'll just write density as a lowercase d, sometimes a capital D, but density as d equals mass divided by volume is what the m and the v stand for. Throughout the next slide or two, we'll explore what these calculations look like. All right, so as we were just saying, the formula for density is mass divided by volume. You may have seen a column like the one on the picture here before, where liquids that have different densities are poured into a column, and they don't mix with each other, and they tend to stack on top of each other, with the most dense liquid being at the bottom and the least dense liquid being on the top, and they separate out into these layers of density, and they often add color to them, as you can see, so that you can really see the division in each liquid. When we are calculating density, we will need to measure the mass and the volume to get the calculation as is part of the formula. Mass is often measured in grams for smaller samples for lab size samples say. And it often will be measured in kilograms as well, kilograms being for more large, maybe industrial commercial size samples. Volumes are typically measured in milliliters or centimeters cubed, which is important to note are the same thing or are convertible. 1 milliliter is 1 centimeter cubed. Centimeter cubed is really standardized for healthcare. If you've ever heard the term cc, 10 cc's of some liquid, that is referring to the cubic centimeter, which is also again referring to a milliliter. We also may see liters as some of the volume measurements, as well as meters cubed. And so when you calculate density, you mix these units as well, and you will see the values for density having units similar to or the same as that you see here, but this is not an exhaustive list. You can have a lot more different units for density. But some examples are grams per milliliter, grams per centimeter cubed, or grams per cubic centimeter, kilograms per liter, and kilograms per meter cubed. I put this slide in here to really dig down into the actual meaning of these units and how the terminology is used and what they kind of mean in that real world scenario. So hopefully it becomes a little bit more clear for you. I think if you understand what a unit is actually saying, a lot of chemistry becomes much easier. So here we have our two densities of two different materials represented. We have the density of water on the left side and the density of gold on the right side. So we have the representation of what a cubic centimeter actually is. So if you can imagine maybe a small plastic box, and that box is exactly cubic, meaning all of its sides have the same length and every angle would then be 90 degrees. And all of those sides had a length of 1 centimeter, so about the length of a staple. Then that box would have a volume of 1 centimeter cubed, and that is the same thing as a milliliter. That's how much size is in a cubic centimeter or a milliliter. If you were to fill that box with water, the water that you put in there would have a volume of 1 milliliter or a volume of 1 centimeter cubed. And that water would have a mass of 1 gram. So if you transferred it to a balance somewhere, it would come up to 1. And that's what the density of water is telling you, that 1 gram of water fills a volume of 1 milliliter. And it's read like this. It's read anytime you see that division in the unit symbol, you always say 1 gram per milliliter. You've used this in your everyday life if you've ever driven a car when you talk about miles per hour. If you were to see that written out kind of scientifically, it would be miles divided by hour. And of course, that tells you how many miles in 1 hour you are going to travel at that speed. Similarly, we have the density of gold here on the right side. So typically, the number is more associated with the top unit in those unit divisors, and so you would say 19.3 grams per milliliter. So again, if you had a cube of solid gold and it was that same exact size, about 1 milliliter on, 1 centimeter on each side, about the length of a staple on each side, that cube, if you were to take it and put it on a balance, would be 19.3 grams. And so we say the density of gold is 19.3 grams per milliliter. Okay, so we're going to start doing some of the calculations with the density formula. This question asks, what is the density of silver if a sample that has 59.6 cubic centimeters of volume has a mass of 625.2 grams? When I do these problems, I like to start by writing out my formula. Density equals mass divided by volume. And I like to list my variables, and volume equals. So I can see from the problem that I'm being asked for the density. The mass that I am given is 625.2 grams.
I know that because it says a mass of 625.2, and I also know that grams is a unit for mass. I see that the volume given is 59.6 centimeters cubed. And so then I can start on my density formula. Density equals mass divided by volume. I'll replace my mass with the number given, 625.2 grams divided by 59.6 centimeters cubed for the volume. When I divide that out in my calculator, it becomes 10.5, and the units on that will be grams per centimeter cubed. So 1 centimeter cubed, or 1 milliliter of silver, should have a mass of 10.5 grams. This problem asks, what is the density of water if 540 milliliters of water has a mass of 540 grams? Again, I like to list out the formula that I'm going to be using. In this case, it is the density formula. Density equals mass divided by volume. We're being asked the density, and we were given the mass and the volume. The mass that we're given from the problem is 540 grams. The volume, even if it doesn't expressly say so, I know that milliliters is a volume measurement, so my volume given in the problem is 540 milliliters. If I rewrite everything, the density is equal to the mass, 540 grams, divided by the volume, 540 milliliters. And anything divided by itself is 1, so the answer, the magnitude will be 1, and the units will be grams per milliliter. And the density of 1 does happen to be 1 gram per milliliter. 1 milliliter of water has a mass of 1 gram. This question asks, a piece of wood is measured to have a mass of 14 kilograms and it occupies 3.5 meters cubed of volume. What is the density of this piece of wood? So again, we're going to start with writing down our density formula. Density equals mass divided by volume. Listing out our variables, we're asked to find density. We're given a mass and a volume. The mass that we're given is 14 kilograms, and the volume that we're given is 3.5 meters cubed. We rewrite our density formula. Density equals the mass, 14 kilograms, divided by the volume, 3.5 meters cubed. And so if we input 14 divided by 3.5 in our calculator, we find out that this piece of wood has a density of 4 kilograms per meters cubed. Another density problem for us here. This one asks, what is the density of a liquid with a volume of 7.435 liters and a mass of 1.2 kilograms? We're being asked to find the density, and we see that the mass we are given from the problem is 1.2 kilograms, and the volume specified by the problem is 7.435 liters. So if we set up our formula, density equals the mass, 1.2 kilograms, divided by the volume, 7.435 liters. If we divide that out, the density becomes 1.2 divided by 7.435 equals 0.16. And our units is going to be kilograms per liter. This problem asks, calculate the density of sulfuric acid if 35.4 milliliters of the acid weighs 65.14 grams. As always, we will start by writing out our formula and noting our variables. Our mass given in the problem is 65.14 grams, and the volume listed is 35.4 milliliters. Therefore, when we set up our formula, it becomes the mass 65.14 grams divided by 35.4 milliliters. Putting 65.14 divided by 35.4 into our calculator shows us that the density of sulfuric acid is 1.84 grams per milliliter. This question asks, what is the density of ethanol, which is more commonly known as the drinking type of alcohol, if 65 milliliters has a mass of 51.285 grams? Our density formula is density equals mass divided by volume. We're being asked to find the density. The mass specified by the problem is 51.285 grams, and the volume given to us is 65 milliliters. So setting up our formula gives us 51.285 grams divided by 65 milliliters. Putting 51.285 divided by 65 into our calculators tells us that the density of ethanol is 0.789 grams per milliliter. Mercury metal is poured into a graduated cylinder that it holds exactly 22.5 milliliters. The mercury used to fill the cylinder weighs 306.0 grams. From this information, calculate the density of mercury. Our formula, D equals M divided by V. We're being asked to find the density. The mass of our sample is 306.0 grams. The volume of our sample is 22.5 milliliters. Setting up our formula, the density becomes 306.0 grams divided by 22.5 milliliters. Putting 306 divided by 22.5 into our calculators returns a density of 13.6 grams per milliliter. This question asks, what is the volume of a gold bar that has a mass of 435 grams? The density of gold is 19.32 grams per centimeter cubed. So we see a little bit of a difference this time. We are given the density and we are given a mass and we are asked to find a volume. So we're still going to use the density formula to solve this problem. We're going to write out D equals mass divided by volume, and we're going to list out the variables that we're given. This time we're given the density, 19.32 grams per centimeter cubed. We're given a mass, 435 grams, and we're asked to find a volume. So if we set up our formula like normal, D equals mass divided by volume, and then replace the information that we know, our new formula looks like this: 19.32 grams per centimeter cubed equals 435 grams divided by some unknown volume. Now we have to do some algebra to solve for the unknown volume. To solve a problem like this, you simply switch the numerator and what is on the other side of the equals sign, so the new equation becomes volume equals 435 grams divided by 19.32 grams per centimeter cubed. Then if we put 435 divided by 19.32, we see that the volume is going to be 22.5. And the volume specified by the units is centimeters cubed. So our volume here will be 22.5 centimeters cubed. So a gold bar that weighs 435 grams will have a volume of 22.5 centimeters cubed. This question asks, what is the volume of a 1,292.43 gram sample of water? And water's density is given as 1 gram per milliliter. If we write out our formula, as always, density equals mass divided by volume, and list our variables. Density is 1 gram per milliliter. Mass given in the problem is 1,292.43 grams. Volume is what we are tasked with finding. We'll rewrite our formula and then rewrite it again, replacing with things we know. 1 gram per milliliter is equal to 1,292.43 grams divided by some unknown volume. Again, the algebra works out for problems with unknowns in the denominator. You just switch the denominator and what is on the other side of the equal sign. So V then becomes 1,292.43 grams divided by 1 gram per milliliter, which will give us a volume of 1,292.43, and we can see that the units of volume from our density mixed volume is milliliters. So the answer is 1,292.43 milliliters. We have another problem of the same type. What is the volume of a sample of copper that has a mass of 13.4 grams, given the density of copper to be 8.2 grams per milliliter? So we're going to write out our formula again here. Density equals mass divided by volume. The mass given by the problem is 13.4 grams. The volume is what we are being asked to find, and then we are given the density to be 8.2 grams per milliliter. And so if we rewrite our formula, replacing the variables with the known values, we get 8.2 grams per milliliter equals a mass of 13.4 grams divided by an unknown volume. And then if we switch the denominator for what's on the other side of the equal sign, the algebra tells us that if we divide 13.4 grams by the density of 8.2 grams per milliliter, we should be able to solve for our volume. And so punching 13.4 divided by 8.2 in our calculator, we see that the volume should be 1.63. And our units for volume in our density units is milliliters, so 1.63 milliliters would be the volume of our copper sample. This question is now a little bit different. This time we're asked to find the mass given a volume and a density. So it says, how much mass would a 35.3 milliliter sample of iron have, given iron's density to be 7.87 grams per milliliter? So as always, we'll start by writing out our formula. Density equals mass divided by volume. Density is given to us as 7.87 grams per milliliter. The mass is not given to us. It is what we're trying to solve for in this problem, and the volume is listed as 35.3 milliliters. So if we set up our formula and replace the variables with the information we know, 7.87 grams per milliliter is equal to some unknown mass divided by 35.3 milliliters worth of volume. I'm going to rewrite that problem so I can show you the algebra. 7.87 equals m divided by 35.3. So when we do a problem like this, we want to get m by himself and we want to get rid of the 35.3. To do so, we will multiply both sides by that number. So we will multiply by 35.3 here, and we will multiply by 35.3 here. What that does is it cancels out the 35.3 on the side with the variable. So there we can now say that m is equal to 7.87 times 35.3. But we don't want to forget our units, so we'll put them back in there. 7.87 grams per milliliter times 35.3 milliliters. We will multiply 7.87 by 35.3, and we'll see that the answer is 277.8. And since we're talking about mass, and we'll also see that these milliliters will cancel out here, we're left with grams as our mass unit. So the answer to our problem is 277.8 grams. This question asks, what would be the mass of a 354.32 liter sample of water, given water's density to be 1 kilogram per liter? And so, as always, we're going to write out our density formula. Density equals mass divided by volume. Density is given to us as 1 because we're talking about water, 1 kilogram per liter in this instance. A mass is what we are trying to determine, and a volume is given to us as 354.32 liters. So if we set up our formula with everything we know, 1 kilogram per liter is equal to some unknown mass divided by 354.32 liters. Just as we just discussed, we'll multiply both sides by the 354.32, meaning that our problem will be 1 kilogram per liter times 354.32 liters. Multiplying those together gives us 354.32. And since we're looking for a mass here and our liters should cancel out, kilograms is the unit of mass given to us by the density unit. So our mass is 354.32 kilograms. One more problem of this sort to wrap things up. So how much mass would a platinum ingot with a volume of 0.3218 meters cubed have? The density of platinum is 21,450 kilograms per meters cubed, a rather dense substance. So we're going to start with our formula written out. Density equals mass divided by volume. We'll write our variables that we do know out. Density is given to us as 21,450 kilograms per meter cubed. And the mass is being asked for. The volume is equal to 0.3218 meters cubed. And so we'll set up our formula with the things we know, 21,450 kilograms per meter cubed is equal to some unknown mass divided by 0.3218 meters cubed. We've already seen how we'll multiply both sides by the 0.3218, and so therefore our expression for mass becomes 21,450 kilograms per meter cubed times 0.3218 meters cubed. The mass answer will then become 21,450 times 0.3218, 6,000 902.6. The units on that, the units of mass from the density value is kilograms. So our platinum ingot would have a mass of 6,902.6 kilograms.